So the thing when it comes to what you think of as equilibrium usually would be equality. In science, equilibrium means that ratios are the same at equilibrium. For example, there are certain hormonal levels or certain, if you guys remember from biology, the potassium sodium transport chain that allows you to move your muscles one way or the other. If you run out of one of those nutrients, then you know that chain isn't going to be able to work, and that can cause your heart to seize up and not actually you know, contract like it should. All of these systems in your body are meant to be at an equilibrium. If something goes wrong one way, your body has replacements and things to fix that. So that's equilibrium in science. For example, let's say that we had, let's see if I can draw this. Probably not. But let's say that we had a certain bucket like this and a bucket like this. And this person here had a coffee mug like this, and this person here had a coffee mug like this, right? So two different sized buckets and two different sized coffee cups. Eventually, if each of them were scooping out coffee from this or water from this, right? And this one scoops it out and pours it into here. This one scoops it out and pours it into here. Eventually, the levels in here would get to a point where the same amount in the coffee mug each time, this one amount in here and the amount in this coffee cup being poured into here would equal each other. That's equilibrium. Does that mean that the amount of volume of water in here is the same as the volume in here? No. It means that the rate of water being poured out of here into here is equal to the rate of water being poured out of here into here. That's equilibrium. For us to understand that, we have to understand that reactions go both ways. An easy way to do this is to think about, for example, silver nitrate in a supersaturated solution. So you have a solution of silver nitrate and you have crystals on the bottom of that. As time goes on, that will dissolve into this, right? That's what we're used to seeing. That dissolving into silver ions and nitrate ions. Now, if it's saturated, what that means is that we have some of those crystals on the bottom. Right? Well, at that surface of that heap, that crystal heap, right? That mound, some of the silver nitrate solid is going into solution. And some of the ions are coming together and crystallizing on the surface of that. If the amount going into solution and the amount crystallizing are the same, that would be at equilibrium. That makes sense? I actually have a 15-year-old rock candy in here. That one's what? That's a good reason to look at, right? So if we take a look at the bottom of this flask right here, you can see that white solid that's basically moving, right? As I move this, it pours. Now that white solid is not the same as it was yesterday. Some of the crystals in there, some of the The ions on there have gone into solution and others have recrystallized. So that is constantly changing. Now the amounts aren't constantly changing, but the actual particles themselves, that'll keep changing over time. Even though it looks the same, on the macroscopic scale, it's going under what we call dynamic equilibrium. What does dynamic mean? There's something called dynamic motion, but dynamic itself, the word, the dynamic character in a story. Yeah, they're the character that undergoes change, right? They're the characters that undergo change. So that is dynamic, but it's still equal, meaning it's constantly changing, but the amounts, the ratios are the same. So it's hard to see. That makes for what we call the reversible arrow. So we have the forward reaction going this way and the reverse reaction going this way. We are used to a lot of like one-way reactions. For example, we take paper, we light it on fire, it goes up into carbon dioxide, carbon, and water. Then what happens? Well, a tree then has to take water and carbon dioxide and make it into the tree itself, which can then become paper again. We're used to those type of reactions. Other reactions don't work in the same way. Maybe if we enclose a system, we'll have forward and reverse reactions working, simultaneously. So that is the goal, just to understand that we have those. Now, what can we figure out? Well, we can figure out the ratio of products at equilibrium to the ratio of reactants at equilibrium. To do this, we set up what's called the K expression. Now, K expression is at equilibrium, so we'll call that K sub EQ. A Q expression is exactly the same thing, except it may not be at equilibrium. A Q could be any second that you slice. For example, in our rate laws, we talked about instantaneous, like initial. We talked about initial rate, right? So if we slice that right there at the start of it, we're definitely going to have more reactants than products probably as the reaction tries to move forward. If we sit there and cut it at the end of it, then we'd have more products than reactants, right? But if we just let this whole thing go until it reaches equilibrium, at that point, we have the ratio of products to reactants at equilibrium. So that would not change after that point, after it reaches equilibrium. Can I make it more focused? You want A or you want B? B or do you want C? C or D? B's good. All right, there we go. Cool. So I said K sub EQ is equal to products over reactants. That's the basics. So this is gas and this is gas. PCl3, Cl2, PCl5. What do the brackets mean? Molarity, concentration, right? Oh. So that's easy enough. So you do B. I'm gonna grab a drink real quick. I feel a tickle in my throat. Hudson, what's different about A and B?
Well, instead of breaking it down into two products, you start with the two products and you make it one.
Mm. So you want to talk about how this is a decomposition and this is a synthesis?
Yeah.
I'll accept that. That is different. Anybody else see anything different there? That's what he's saying. There's a coefficient. So this means for every 1 mole of this that breaks down, we get 1 mole of this and 1 mole of this. For this, every 1 mole of this is 2 moles of this. Now, for the rate law problems we did, you had to find the order by looking at data. For finding the K sub EQ here, this K sub EQ, the constant at equilibrium, the coefficient becomes an exponent. We don't call this order, but it becomes the exponent there. So it's products over reactants, but each of these ones is to the power of 1, and this one is because it's a coefficient of 2 to the power of 2. So go ahead and do C real quick. Remember, this is the easy part of the unit. This is the part that looks very easy. So you're like, oh, I get it. But tomorrow, remember how this looks always on the next day. Wait, what did you just do? Right? Every single unit starts off very easy. Then we start bringing in the other ideas and concepts. It's like, this one will have one of the hardest things that you guys will ever do. You guys know the quadratic formula, don't you? Yeah, then you're good. That's not comforting. Yeah. No. Yeah. Basically, you'll have to find an X, but the X can be one of 2 X's, right? Luckily for us, it'll always be the positive because you can't have a negative concentration, right? Negative positive. Yep. All right. You got it. NH3 up top squared. N2 and H2 down bottom. Easy enough. Let's do D. What's different between D and all? I'm sorry, we need to cube that. What's different between D and the rest of them? It has a solid. So does a solid really have a concentration? No. So solid always goes in as 1. It's either there, it's not. Oh, that looks too much like an I, doesn't it? As a 1. We don't have to write this. Concentrations work for aqueous, moles per liter, or gases, moles per liter as well. Solids and liquids are either there or they're not. So they are written as 1. So this one right here will be K sub EQ equals C2H5OH over 1. This will be homework for Monday. I'll post up the answers. Let me ask you this. We're going to start putting some numbers in there. If K sub BQ is greater than 1, do we have more products or more reactants? More products, because products is on top. So we would say the products are favored. If K sub BQ is less than 1, more reactants, because you have a bigger number divided by a smaller number, like a smaller number divided by a bigger number. So we would say reactants are favored. Reactants are favored. So let us put some numbers in here. So K equals HI squared, H2. Why am I not putting the I down there? Because it's solid. So now all we do, 0.015 square, and then 0.060. So we have molarity squared over molarity, which will. Why can I not read? Oh, yeah, I can't read. Thank you. I need to switch those. HI is the 0.060. Thank you. And the bottom is 0.015. 0.060 squared divided by 0.015.
The answer is 0.24.
0.24 molarity squared per mole divided by molarity would be molarity, but we don't usually look at K's unit. No, we actually just we don't even put them usually.
Oh.
Yep, it's just a number. Products or reactants favored at equilibrium? Reactants favored. Because K sub BQ is less than 1. Yep. Go ahead and try 2 or 3. I'll give you a few minutes to do that. 2 and 3.
I was just wondering if, like, since it's aqueous, it would just be 1, or if we do it like normal, like we did with the gases.
Yeah, so aqueous and gases have concentrations, solids and liquids do not.
Okay, thank you.
You're welcome. So let me do the reading a little bit closer for this one. K sub BQ equals products over reactants. So we have H plus, NO2 negative, all over HNO2. That equals, oh, they give us K. So what do we want to do? We want to rearrange this equation to solve for HNO2. So we multiply both sides by HNO2 and divide both sides by KEQ. So that equals 0.00071. Yeah, who's favored here? Products or reactants? Reactants, because K is again less than 1. Oh, look at this. It's the same thing, 0.019. And that can actually be common, that these two things be the same thing. Because what you have happening here is HNO2 is splitting into H plus and NO2, right? So whatever the concentration of this was, right? depending on these guys, that it's going to lose the same number of H pluses as NO2s are being formed, right? As this one thing breaks down. So 0.19 times it's 0.019, thank you. 0.019 times 0.019 divided by 0.00071.
That would be about 0.5084.
And two significant digits, 0.51 molar concentration for HNO2.
Oh.
Two significant digits, yep. What's the number that doesn't matter in this one? 3 grams, because it is solid. So we have K equals Al3 plus OH negative to the third power. We want to solve for Al3 plus. So we are going to divide both sides by OH negative to the third power. That's going to cancel out. We have the K as 1.9 times 10 to the negative 33rd. Who's favored at this at equilibrium here? Huh? Still reactants. That's a very, very, very small number. What this is telling us in reality, do you guys remember whether something's soluble or insoluble from last semester? Yeah, right? Let's take a look. What this is aluminum hydroxide dissolving. Aluminum hydroxide is soluble, so not a lot of it really will dissolve. That's why this is so big, or I'm sorry, so tiny a number. So 1.9 times 10 to the negative 33rd divided by 8.7 times 10 to the negative 9th cubed. Oops, that's not cubed. Is there a cube button? Nope. Looks like I have to use a caret thing. Scientific notation tells me the concentration of Al3 plus is going to be 2.8, actually 2.9 times 10 to the negative 9th. 2.9 times 3.
That would be 8.7.
So that makes sense then too, because this is breaking down. The concentration of the aluminum, or actually the concentration of the hydroxide, is 3 times more than the concentration of the aluminum. Bring your calculator up here.
Oh, yeah, I didn't do that.
You didn't cube.
Yeah. we get to a certain way, there's some brackets around it.
I didn't put brackets around it.
So if you just don't want to-
Oh, did that act weird?
Yeah, I think so.
Yeah, you have to put brackets around 8.7. Or parentheses.
I didn't.
Oh, good.
Texas Instruments, yeah, 84, what?
Oh, I have.
Oh, yeah, no, it doesn't matter.
You're making things up here. All right. Consider the reversible reaction, blah. If we have the following concentrations. So this is K. We don't know if we're at K or not. We have this reversible reaction. We have these amounts. We don't know if we're at equilibrium. So that's what they want to check. So we actually don't use K here. We use Q instead. I'm going to get rid of that and put a new Q. Oh no. Am I out of this stuff? It's the second one of these I ran out of today. No, it doesn't look like it's. There we go. Oh, it's just having trouble grabbing onto the friction. All right. So Q equals the same thing.
Wait, you, what is that?
Yeah, but this-
So K is at equilibrium. Q can be at any time at all. Q stands for the quotient. We said it right here. You have the K expression, which is also the Q expression, which is the same thing. K is at equilibrium. It's K sub EQ. Q is just anytime. We don't know if it's equilibrium or not. It could be. Well, if you're not at K, you can't use K, right? Because K is only at equilibrium.
Why are you?
That's at equilibrium. So this, we don't know. Maybe it is at equilibrium. We don't know yet.
look, you know, you want
Oh, thanks.
to-
Everybody talking to me, right? No, there we go. PCL5. Thank you. So Q, does everybody get Q? Q is the quotient. It can be at any time. All right. Yes, if you're at equilibrium, it's KEQ. Any other time, you use Q. If you don't know, you use Q. K is, it's K sub EQ.
Oh,
I just wrote it so many times that we all understood. Yeah. Yeah. 0.10. And at the bottom, 0.05, 0.0050. We don't have to square anything, do we? 0.25 times 0.1 divided by 0.005.
It's 5.
It's 5. So what you guys got? Am I at equilibrium? Currently, are the reactants, is there more reactants or products currently? Which one is favored? Products. But the K for this says that we should even favor the products even what? More. So which reaction rate do you think is going faster? The forward reaction rate or the reverse reaction rate? The forward reaction. The forward reaction is going faster because we're going to get to a ratio of 150 to 1. Currently, we are at 5 products to 1 reactant. We need to get to 150 products to 1 reactant. That's what this ratio is telling us. Yeah. So we are at 5 to 1 products to reactant ratio wise. We need to get 150 to 1. So which reaction makes more products? The forward reaction makes more products, right? Forward reaction makes products. Reverse reaction makes reactants. That's what it says down here. Under part C, problem 1, you calculated Q equaling 5. You concluded that this reaction is not at equilibrium because it did not equal. If Q is less than K, forward reaction favored. If Q is greater than K, then what happens? Reverse reaction is favored. The system is constantly going to equilibrium. When you look at the system, that's what Q is. That's when you're that's what Q is. If you know the system has reached equilibrium, then you know you're at K, right? Try number 2 on your own. Really? That's weird. So this should be your setup. 0.0005 divided by 0.015 divided by 0.02 square.
The answer is 83.3333.
Two significant digits, so we get 83. Are we at equilibrium? Yes, we are at equilibrium. Questions here?
So, this command that is Q is greater than K, so this reaction is greater. What if Q is
Then we're at equilibrium.
no more reaction?
Each reaction is going at the same rate.
Okay.
At equilibrium, each reaction is going the same rate, right? So let's do that. Q equal to K. The rates are equal. Forward and reverse are equal. Now, what does that mean though? If Q is equal to K, the rates are equal. But if K is over 1, then products are still favored at equilibrium, right? The rates may be equal, but you could still have more products than reactants or more reactants than products. Right. So this will actually be Monday's work for Tuesday. You can obviously, get it all done tonight or whatever, or in the rest of the period. As I look through there, the only thing that's a little bit different is look at number 8. They give you volume and they give you moles. So before you plug this into the equation, oh, well, it's 0.66 moles per 1 liter. They could give you a different volume or something like that, and you would have to calculate molarity before you plug it into this, right? Does that make sense? Did you say, oh my gosh?
Oh, gotcha. So it's not more.
Yeah.
Oh, this is perfect.
So that's the assignment for actually Monday as well. What I'll do is I'll go ahead and post on there on Monday, post the answers to this. That way you can check your work. If you have questions, by all means, stick around. Otherwise, have a great weekend, guys. One more week down, right? 4.5 weeks. Grades next week. Midterm. So there's not much time left here. Take care of yourselves. Take care of others.